Good afternoon, everyone. I don't know if it's good afternoon for everybody, but here in Denmark, where we are, it's good afternoon. Welcome to our webinar. It's our second webinar this year. Today we are going to talk about newborn hearing screening equipment and what you might not know about the ABR stimulus level. My name is Mariana Rosling Jensen. I'm an education and training manager at Autometrics. Our presenter today is going to be Niels Westerlund, which is he's a product manager here at Autometrics, but he will introduce himself. I'm here because I want to tell you some tips and tricks about the webinar. All participants are muted just to reduce the background noise. It's possible to ask questions during the webinar. You can go in your screen and write down a question. I will be selecting the questions in the end of the webinar where Niels will answer for us. If we don't manage to answer all the questions, then after the webinar, we will write to you an email where we can send you the answer for your question. If you have any technical problems, and you need some support, please let me know. Now I will hand over to Niels, who will be presenting for you.
Thank you very much. Thank you. As Mariana just said, my name is Niels Westerlund. My background is in signal processing, and I've been in the hearing aid industry for more or less between 7 and 10 years, depending on how you count. And today I'm as Mariana just said, the international product manager for the Madsen EchoScreen infant hearing screening device that we sell all over the world. And this presentation is going to be about ABR screening levels or stimulus levels. We have known for quite some time that screening devices in the market, they have different stimulus levels, because the 0 dB threshold of newborns is not well defined, or it's not defined. And different screening device manufacturers address this issue in many different ways. And of course, these are obviously how they address these issues is kept secret. No official standards exist today. But of course, if we have different stimulus levels when measuring ABR, this may cause screening site and end user confusion. And we can have two different screening devices with the same nominal level that might generate different refer rates, given that they have similar algorithms or detection algorithms. So, and furthermore, different manufacturers use different ABR stimulus types, both regarding time domain differences and frequency contain. And this is a fact that renders an objective level comparison really difficult. So what we want to do, or what we wanted to do in this study, is to identify a subjective ABR stimulus level difference between the Madsen EchoScreen and two of the most widely used infant screening devices on the market. So instead of doing a technical measurement and risk comparing apples and pears, we wanted to do this subjective threshold measurement using real ears, real adult ears, to try to find these differences. And as I said, three different ABR stimuli was compared. The EchoScreen with our own standard dome-shaped ear couplers that are widely used all over the world, and two competitors that were set up using their standard setup with their couplers, so on. So the first question that arose when we started thinking about this was, how do we present the device ABR stimulus reliably to an adult ear? Because we cannot fit a baby coupler to an adult ear, at least not a normal adult ear. And we also want the acoustical effect from the ear coupler to be removed. We don't want, what we want is we want to have the acoustical effect from the ear coupler in the measurement. and that signal should be sent into the adult ear. But however, we need to present the stimuli via ordinary earphones, in this case HDA 200 earphones, but we need to get rid of the acoustical influence from these earphones. So the question is, how do we do this? Well, first of all, we of course need to record the device ABR stimuli. Can I change? Yeah. Where do you do that? Okay. So we need to record the device ABR stimuli to be able to present it to the test subject ears. So we need an ear simulator set up for recording. And we need also to eliminate the acoustical effect from this ear simulator to achieve a pristine ABR stimulus signal. So in other words, we want to get rid of the ear simulator, and we want to get rid of the HDA 200 earphone acoustical influence when we present the stimuli to the adult ear. So if we sum this up, we end up with this. Okay. So we need also, of course, some hardware. And what we did to be able to attach ear couplers and the HDA 200 earphones to the 711 ear simulator, we constructed this custom-made faceplate for mounting these circumaural headphones or couplers to the 711 coupler. And that was the only specially built hardware we had during this measurement. I also listed all the hardware we used, the preamplifiers and microphones and stuff like that, but I won't go into detail about that. So, how did we do this in practice? Well, first of all, we need to identify a system that is represented by a pair of HDA 200 earphones attached to the 711 coupler. And we did this by using or sending in a chirp through the HDA 200 at a 48 kilohertz sampler frequency, and we did a separate system identification for the left and right channel in the earphones. And then we calculated the inverse filter of this system. The next step was to apply the ABR stimulus via ear couplers through the 711 coupler and record this signal. And all the devices were set to a nominal level of 35 dB NHL. So the next step, if you add these two systems together, we end up with a signal chain that looks like this. And if you go into detail and look at these systems, we can see that we actually have the inverse of the HDA 200 and the 711 coupler here, which is done as an offline filtering. And this results when we take the recorded signal from the AccuScreen or some of the other devices and send it through this inverse filter and present the output from that inverse filter to the HDA 200, we end up with a pristine ABR signal, because we end up actually with two unity systems that does not affect the output signal. So that was the method we used to be able to take a screening device output signal that is being sent through an ear coupler, and then it is, from a signal processing point of view, it is totally unaffected when it enters the ear. We also did a standard click stimulus for reference. There is a standard called ISO 389-6-2007 that specifies that if we feed HDA 200 earphones with a 100 microsecond square click at the rate of 20 clicks per second at a certain voltage, we end up with 28 dB sound pressure level. And we generated such a click sequence as a reference signal and added this to this test signal battery. So in other words, we end up with 4 signals that we want to find the threshold for. The reference click that I've just mentioned here, the AccuScreen, and 2 competitors. This is a plot of the resulting spectra, the original spectra from the AccuScreen in this case, that is the black line, and the click spectrum that we have done this inverse filtering on. So ideally, these curves should be exactly the same if we did a good job. And as you can see in this plot, we did a good job between like 1100 up to 7000 hertz, roughly. So if we move on to the next step, where we have now collected all data we need, and now the idea is to present this data to human test subjects. So this HDA200 input signals were stored as WAV files in the speech library of an Astera audiometer. We invited 28 adult subjects to participate in this study, age from 25 to 49, and we ended up finding 21 male and 7 female subjects. Of course, we checked the ear canal first before testing, and then we did an initial pure tone audiometry to ensure a normal hearing. This was done using the modified Hughes and Westlake method. And the inclusion criteria for being a good candidate for this test was that we wanted the tone threshold range not to exceed 10 decibels. So we wanted a relatively flat hearing curve. And we found 37 ears that fulfilled the criterion for inclusion in this test. So the ABR stimuli were presented by an Astera using the AutoSuite speech module. The presentation order was randomized among subjects. The testing left-right was also randomized. And these modified sound files, or the click sound files, were loaded just like any other speech material and presented continuously. So we did not alter the rate of the clicks from the devices. We recorded I think 30 seconds, and then we repeated that 10 times. So we have exactly a native pristine signal from each screening device. The result was quite interesting, and there are a lot of numbers on this slide, but I'm going to walk you through it. If you start with the reference click, the leftmost bar, that is the reference click I talked about, where a certain signal, a square signal with 100 microseconds duration, results in a known sound pressure level. So this is just for reference and an equality measure. So if we have done a good job, the leftmost bar should be 0 dB. When doing the measurements, we ended up at 0.51 dB, but this is, I mean, the confidence interval from this measurement covers 0 dB, so we could just as well end up at 0 dB. So we know that we're doing things right. If we move on to the AccuScreen, we ended up at minus 5.43 decibels. And as you can see, the confidence interval is relatively small. But the most interesting thing is to compare this, of course, to our competitors or colleagues in the market. If we take competitor 1, we can see that we ended up at minus 22.46 decibels on those. And competitor 2, we ended up at minus 12 decibels. So as you can see from the AccuScreen and competitor 2, we end up with sort of 7 dBs difference in threshold level. And we can also see from the table below that we have a relatively small standard deviation, so it was a relatively stable measurement between subjects. And if we move on to the next slide with conclusions and discussion, I think we know from this investigation that there is a difference between nominally equal ABR stimulus levels used by different newborn hearing screening devices on the market. And we also know from this data that these differences are statistically significant at the 95% level. So we know there is a difference. And if you move on to discuss what this really means for the end user, for the screener or the screener program manager, of course these differences should be taken into consideration. For instance, when switching between screening devices. And I'm not saying that someone is doing right and someone is doing wrong. It's just a matter of different definitions, how we define the 0 dB NHL for a newborn. And given that these devices use the similar detection algorithm, these differences may pose a problem. Because of course, if you had the same algorithm and one screening device screens at 7 or even 7 dBs higher stimulus level, then that system will have a lower refer rate, obviously. So proper and reliable information about this to screening programs is necessary, I would say. And also, these differences that we see in this study may explain at least some of the discrepancies in refer rates we see when screening programs switch hardware from one manufacturer to the other. And this must be taken into consideration. So that was the presentation, and I guess we have time for questions.
Yes, we do have time for questions, but I haven't received any questions yet. So I will ask a question. How important is the size of the ear of the baby? Because we know that the stimulus is going to be different depending on the size of the ear of the baby. So do you know how important, how much different this is going to make? Do we take this into account when we measure?
Well, in this measure we did not, of course, because we mounted the ear coupler on a flat face plate. The effect of a pinna is, of course, a part of this investigation because we placed the HDA 200 on the ear, and of course we have a pinna around the ear. But if you talk about sound pressure level, the size of the pinna, of course, have an effect, because if you have let's say you have an extremely large pinna that you squeeze into a small air coupler, the effective air volume will be smaller. So of course you will end up with a higher sound pressure level. That's basic physics. And I don't know the exact effect in numbers, but I wouldn't say it's critical.
No, but not of the pinna, but more of the ear canal, because we know that the children, the small baby's ear canal is very small, so the sound pressure level at the eardrum will be higher than the sound pressure level would be in an adult. So I'm just thinking, when we are talking about testing babies, so do we have any study or anything that show what is the sound pressure level in the ear of the baby?
I'm trying to remember if I have seen such a study,
yeah.
And I can't recall it, but I know that there have been some studies about differences between adult ears and newborn
yes,
ears.
It will. There's 20 dB difference in the higher frequencies.
Yeah.
That's why I'm asking. So now we are talking about the stimulus. What does it mean in the baby ear?
Well, the purpose of the study was to find the relative difference, of course. So it's sort of out of scope. So I don't really have a good answer to you.
No.
I mean, given the study setup, the interesting thing is to see what is the difference between different devices.
I have another question for you. Children with malformed ear, is their bone conduction facility? If we have a child with a malformed ear, would it be a bone conduction way of doing the test? No, it will not, because when we are working with ABR, with autoacoustic emission, you want the sound to go in and out.
Yeah, but I'm talking about ABR.
ABR, so, yes. Okay, but even though, because they are going to have problems in the middle ear, that will be a refer screening ABR because they have a problem in hearing.
Yeah. Well, it depends on the malformation, I guess. If the outer ear is malformed, then we have a different situation, right?
Yes.
Then you can maybe do something. I mean, excite the ear in some way and get the ABR response. Yeah, but if you have a middle ear or inner ear or middle ear defect that prevents the sound to enter the cochlea.
Yes, exactly, and I think that's what she means. So you will not be able to test, because then the screening is referred, because what we mean with the echo screening is to do a screening. So there is a problem in the ear anyway, and the child should go for assessment of the hearing anyway if there is a malformation of the middle ear.
Yeah, that's the point.
So that will be a refer on the screening, and then you should go for verification find out how is the inner ear and how it's functioning, because this child might need some kind of other helps anyway.
Yeah, if what you're saying is that if you have a deformed ear, you by default you should do a diagnostic.
Exactly,
yeah,
exactly.
You don't need a screen.
You don't need a screen, right, because you by default have referred to the screening. Okay. I can't. Oh, I just received. Can we use the same device for an adult? Can we use echo screen for adults? That's the question.
Well, technically speaking, yes. We have on the echo screen we have the option of doing an ABR, and now I'm talking ABR or OAE, because you have the probe, and on the probe you can fit a foam tip that fits an adult ear. I do it all the time actually in my work, and it will give you a result. It will give an OAE, or you can do an ABR. However, if you do an ABR, it's important to remember that we are actually looking for a wave 5 when we do an ABR in the echo screen, and that wave 5 is actually, the latency is shorter in an adult, so it comes earlier after the sound onset on an adult. However, the echo screen is optimized to look for wave 5 at a specific time. I think it's around 8 milliseconds or so, and that's where you should find the wave 5 in a newborn baby. On an adult you will find it earlier, so there is a slightly higher risk of refer if you test an ABR, do an echo screen ABR test on an adult. OAE is something completely different, of course. Then you can do, then it doesn't matter. But I can also add that the ABR module, or the ABR test in the echo screen, is optimized from, I think it's 34 weeks gestational age up to 6 months. That's what we say in the, that's what it is validated for.
And then another question. Are the stimuli rate used for adults hearing threshold testing? And further, are the same stimuli rate used for adults hearing threshold testing?
So the question is, do we use the same stimulus rate both for babies and adults?
Yeah.
That's a good question. I would say yes. I don't see any reason why we shouldn't use the same.
Yes, yes.
But I don't know. We have the charter,
yes.
And I don't know the details about the charter system. But
and the charter is more diagnostic.
Yeah, it's a diagnostic.
And the
EP.
rate you can change and actually use a different kind of rate. But and I think it's very important to point it out here that we have some devices that are for screening, and we just have a pass and refer, and other devices that are for doing diagnostic.
Absolutely.
And what we are talking about here, it's more about the screening device.
Yeah, it's important to, of course, to separate screening and diagnostic, because those are two totally different workflows. I mean, the screening is something that is automated, a minimal amount of effort from the operator. Basically, you should just have to plug the baby in and press a button, and then you should have a result. Whereas the diagnostic requires a lot of knowledge, a lot of choices, a lot of setup, but also gives you more information, of course.
I can't see any more questions. Then I want to say thank you for Nils to be here today.
Thank you.
I hope you enjoy the webinar this time, and in around a month we will have a new webinar, and this time will be on infection control. Thank you for your participation. Bye.